702 and Cape Talk.
The Naked Scientist.
Good morning, Chris.
Good morning.
Chris, this story fascinates me, our science story of the week. I thought that there's a little bit of a crisis potentially around antibiotics in terms of, what, we're becoming more and more resistant to them. They're over-prescribed by doctors and so forth. But what is this one about?
Well, this is an interesting study because for a long time we've been counselling patients that antibiotics are for treating bacterial infections and that because the majority of colds and runny noses are caused by viruses, then taking antibiotics will do no good whatsoever. So a very interesting paper has emerged in Nature Microbiology this week by researchers at Yale Medical School. This is Akiko Iwasaki, who has a long track record of studying viruses. And they've made the unusual discovery that, in fact, some classes of antibiotic drug can put the body into an antiviral state. So they might actually have an antiviral or cold remedying effect after all. Now, they're not saying we should rush out there and start giving antibiotics for colds. They are saying, though, that the observation's interesting because it might show us how we can find new ways to manage viral infections. Now, in their studies, which they did on mice, admittedly, so you've got to be a little bit cautious about how you translate this to a human, but what they did was to use one class of antibiotics called aminoglycosides. There are agents like neomycin that are members of this family of antibiotics. When mice receive these antibiotics rubbed onto, say, skin or rubbed onto the inside of the nose, they found that cells in the nose were much less easy to infect with viruses afterwards. And the mechanism appears to be that these antibiotic molecules, through a totally different mechanism through which they kill bacteria, trigger the immune cells in the area to start pumping out signals called interferons, which put the adjacent cells into this very profound virus-resistant state. It's like sounding a burglar alarm. As a result, all the cells go into lockdown and you don't grow new viruses in them. So what they're saying is, if we can find out what it is about these molecules, these antibiotic molecules, that make the cells do this, then what we could do is to focus on that aspect of their behaviour and come up with a new class of drugs which will enable us to make antivirus drugs which will be potentially very useful in the treatment of a whole raft of different virus infections, because they tried this against herpes virus that causes cold sores and genital disease. They tried it against Zika virus. They tried it against flu, and it had the same effect against all these viruses. So there may, you never know, be a way to cure the common cold, and the clue may come from antibiotics in the future if we can work out how these molecules are doing this.
Phil in Centurion, good morning to you.
Good morning, Eusebius. Good morning, Dr. Chris Smith. Great show.
Thank you, sir. What's your question for him?
Okay. 2 or 3 weeks ago, as I recall, you said that air is fluid. Did I hear that right? Air is fluid. Could you please explain that scientifically?
Sure, and yeah, good listening. Congratulations. Air is a fluid. Yes, you're right. You did hear correctly. It's a gas, but it's also a fluid, and it behaves as a fluid. And all it is a more spread out fluid. When we have water, we have a much more condensed or higher density fluid. When you have a gas, it behaves in exactly the same way. The molecules are just a bit further apart. But to all intents and purposes, the fluid in the air behaves identically to a stream of water. And you can do this yourself. If you take, say, a spoon and dribble water over the back of it, you'll see it sticking to the surface of the spoon and then coming off at an angle. If you put that same spoon in a wind tunnel and blow smoke over the spoon, which is particles in a gas, you'll see exactly the same trajectory. So the two things behave both physically and mathematically the same.
I still can't get my mind around that, in fact. But your explanation is obviously a good one, but I'm still trying to work it out.
Good luck.
Okay, you can chew. Cheers, Phil. You can chew on that one.
All the best, guys.
Cheers. Thanks so much. Thanks a lot. Hey, let's go to Kenilworth. Caroline, good morning.
Good morning, Eusebius. Thanks as usual for a super program.
Thank you kindly. What's your question?
I'd like to ask Chris. I was baking a cake a couple of weeks ago, and the oven was set at 180 degrees. All of a sudden, the oven door just exploded. And I couldn't understand why. And then I realized that I might have turned my Kenwood Chef mixer on to mix the icing. And Could that have caused the oven door to explode?
What on earth did you put in the cake? That would be my first question. What were you cooking in there? Dynamite or something?
I want to tell you it's a cake that I have baked many, many times. It's an ordinary old carrot cake.
They just don't make carrots like they used to.
No,
No, they obviously don't.
they come laced with dynamite or something. I suspect that you're right. When we heat things up, then as a result of the change in temperature, often the metal in the oven is going to be the first thing to start changing shape the most radically. The metal is going to expand. This is going to change the loading on the fabric of the cooker, how the forces are transferred across it. Glass, the oven door, I presume it's a glass-doored oven, is relatively
It's a
inflexible.
glass oven and it's supposed to be shatterproof glass.
Yeah, but the thing is that the glass is going to be under stress because the thermal changes in the shape of the oven and the metal expanding could apply uneven forces across the door of the oven. A number of things can make a difference to how the glass also responds to heating, because if you get a lot of deposits, I don't know how clean your oven is, you might have a very, very pristine oven door. Many of us, myself included, do not. If you've got deposits on the glass, they can absorb heat asymmetrically, which transfer heat or prevent the transfer of heat into the glass, so the glass doesn't heat symmetrically. So a range of factors, including the expansion of the metal of the oven, the glass not heating symmetrically, the glass becoming a bit older, and then you perhaps having some vibrations, which could make a difference. This is going to lead to possibly resonances in the glass or a focus of force in one place, which could encourage the glass to suddenly give. But my money would be on it being the fact that as the oven gets hot, then you're going to get expansion, shape changes, and uneven loading by forces of the glass, and that's going to focus force in one place and cause it to crack, especially if the glass over time has developed a weakness, because every time you turn the oven on, it heats up and then cools down, and this is going to cause things to expand and contract, and you might get tiny fractures in the glass just because it's getting older, and with repeated use and cleaning and so on, you do get these micro fractures in the surface, and they're going to focus forces at one particular point, which is going to make the glass more likely to go eventually in that place.
Thank you, Caroline. Let's take one from Twitter. Here's one, Chris. Brian has got an interesting one, I think. Brian says, why can I hear my phone's alarm, but not my wife's alarm, and yet she wakes up earlier than I do?
Well, it might be something to do with the frequency that's used, because perhaps Brian doesn't know what he does for a living, but perhaps he has a degree of hearing loss with older age. Perhaps the frequency that the alarm is running at, the sound frequency, he has a relative or a slightly lower sensitivity to than his own phone. If his own phone is closer to him, obviously it's going to be louder, because the further away you are from a sound source, the quieter the sound is. So that might be part of it. We also answered the question a few weeks ago here on the programme, which was, why do I almost wake up before my alarm clock? And we discussed the fact that we're conditioned, because we have a body clock, we get conditioned and into a pattern where we predict what time of day it is, and we use that to optimise our activity. So it might well be he's just very tuned into waking up at that time, and so he's closer to the threshold of waking, so his alarm has an easier job waking him up or whatever, because of the time of day that he's got habituated to being woken at.
Makes sense. Lebo, good morning.
Morning. My question has to do with nerves. Do nerves regenerate?
Crisp question.
In particular,
Yep. Okay, go on.
in particular, I lost my sight, and apparently there was nothing wrong with my eyes. What happened was my nerves were swollen, and then they gave me a steroid called Solumetro, and it brought the swelling down from my nerves. But after the swelling came down, the nerve did not return to their original shape. Hence, I've lost my sight.
Good morning. I'm very sorry to hear about your sight loss. The answer is it depends on which sort of nerves we're talking about, because the body can be considered in two zones. There's the central nervous system, which is your brain and spinal cord, and then the peripheral nervous system, which is nerves around the rest of the body. Now, as a general rule, if you injure nerves in the periphery, so say I injured a finger or, heaven forbid, amputated an arm with a chainsaw or something, if this tissue is promptly reattached and the nerve endings are brought together, nerve cells in the periphery can regrow down the nerve and reconnect to their original target, and you can get back motor function, the ability to move, and you can get back the ability to feel sensation. It takes a while because the nerve takes a while to grow back down the conduit or the path of the old nerve. It uses that as a pathway to find its target, but it definitely happens. Now, in the central nervous system, things are quite different, and the central nervous system it does include the optic nerve. So the problem with with yourself, by the sound of it, is that there's been damage to the optic nerve, and as a result, the nerve cells, although the optic nerve is outside the brain, it's got to connect into the brain substance to make the connections so you can see. And if you've damaged those nerve cells, there's a high likelihood that they won't regrow because the cells that provide the nerve tissue in the first place have been damaged. In other words, the ganglion cells that make the optic nerve may have been damaged irrevocably by the injury, and that may be why it hasn't come back. So the bottom line is that the central nervous system regenerates very poorly, and that's why people who have strokes, for example, do find that they have a limited ability, not a zero ability, but a limited ability to recover. And the stroke is obviously damage to central nervous system tissue. In your case, it sounds like swelling could have caused damage, and that's probably why the nerve cells have not regenerated.
702 and Cape Talk.
The Naked Scientist.
Indeed, we're taking your questions for him from Science. Bongani, good morning.
Yes, good morning, Eusebius. And to the Naked Scientist, good morning.
Good morning, Bongani. What's your question?
Yeah, okay. So my question is this. I'm very interested on the Big Bang Theory. So I've been doing some research in the past few months. So I just wanted to ask the scientists there, because I've been boggling with this question and can't get to the bottom of it. I just want to ask you, what came before the Big Bang Theory? And what is the evidence there as to how do we know, like, that small dot that was spinning smaller than a dot on a paper and everything? Like, how do we know it even existed and all of that stuff? How do I can't get my mind through it. I'm still reading, but I just think the Naked Scientist can explain where did that dot come from and where was it spinning in? What caused it to spin? And is there evidence, or is this just just a sort of belief or whatever? I just need to know with regards to that, please.
What's being referred to here is what happened about 13.8 billion years ago, because that's the time when we believe, based on our current measurements and modelling, that the universe first began to exist. And we think the universe came from a singularity. That's the dot that's being referred to by Bongani here. And we think this singularity is extremely small, but extremely energetic. And for some reason that we don't understand, this energy unleashes, the universe pops into existence and very rapidly begins to inflate like a balloon blowing up. And it inflates very, very fast. And it's very, very hot. And then as the universe inflates and expands, it cools down. As it cools down, then some of this very hot soup of material begins to condense, and you get the first matter. And you get hydrogen, helium, and a tiny bit of lithium. Over time, because all this material is randomly moving around, under gravity it begins to bunch together, and because everything's moving around, it can't not move around, so all the momentum or movement or spinning of these objects and materials coalesces into balls, and that's why the objects, the galaxies, the stars that condense in there, the planets that form around those stars, that's why they're all spinning and turning too, because everything's got momentum, and you have this thing called conservation of angular momentum. The universe then slows down its growth for a bit, and as it ages, though, it's speeding up again. And we know that because if we look far away in the universe, we can see that things are moving away from us, and the further away we look, the faster they're moving away. Evidence that the universe is growing, and as it ages, it's growing faster. Now, what came before the universe, we don't know. No one was there to see it. No one was there to see the beginning of the universe. But we can infer what happened because there are still what people dub the echoes of the Big Bang knocking around in the universe today. There's something called the cosmic microwave background radiation. And this is effectively radiation left over from when those initial phases of the Big Bang happened. And because the universe has stretched out and grown, the light, those radio signals have stretched out and become very long wavelength radiation, but they're still there. And there are signals hidden or written into those radio signals, those microwaves, that we can read today. and they give us clues as to what was happening in the early phases of the Big Bang. So we can work out what was happening, and we can work out roughly when it was happening by looking indirectly at these other measurements and other things that are around today. And physicists are running very complicated simulations saying, well, we know where the galaxies are, give or take today, or many of them. If we put this into a computer, we can model how it must be growing and evolving. And if you can model how it's growing and evolving, getting bigger, you can then wind the clock back to ask what would it have looked like in the early days. And that's what they're doing to try and get a model of where we came from and where we might ultimately end up.
Okay, this is such a highly theoretical question in terms of circumstance, but let's go there from Mike on the SMS line. Is it possible for me to be HIV negative, to have sexual intercourse with someone who's HIV positive? I then test negative thereafter, but nevertheless, I am infectious.
Okay. I mean, first thing, one must be very, very cautious because HIV is transmissible, and one must be very careful about this and don't have unsafe sex, because HIV currently, we have no way of curing people who acquire this virus. So it's not something to take risks
with. That's why I was
with.
hesitant from a public health point of view, but nevertheless, let's deal with it for the moment. Yeah.
Now, the way we test for HIV is a person who has had an exposure in the past or just wants to know their status will supply a blood sample. Now, we tend to look at least 3 months after a person's last potential exposure because it takes time for what we're looking for in our blood tests to register and to be there at a level that means it's safely detectable. And what we look for are antibodies to HIV. We also look for antigen, which is proteins made by the virus as it grows in the body. And so we're effectively looking in 2 different ways at 2 different targets and with several different tests to make sure there are no false positives or false negatives. And if we register a positive, we then go back to the person and we test them again on an independent blood sample to make sure we've got the diagnosis right, because it's possible a test sometimes gives a false positive or a false negative. A test also might be tested or carried out on the wrong blood sample. These things happen. So we always retest. Now, if you do this, the likelihood of getting the wrong result is extremely low because we're using multiple different tests which look for different things. You're coming at the problem from different angles. So it's very unlikely that you're going to miss something. It's not impossible, though, because you can never say never in medicine. And it's also not impossible that somebody could acquire HIV and then shed the virus and then cease to be infected because they have an effective immune response to the virus. And these people do exist, and we occasionally find them. In fact, we think we found somebody in this situation in our hospital recently who had clear evidence of having been HIV positive in the past and appears to have mounted a successful immune response and cleared the infection and has an undetectable virus load in their body. Now, this does happen, but these people are rare. And at the moment we're trying to study them to try and work out how they do this, because if the immune system's capable of doing this, which it clearly is, it might be possible to try and find a way to persuade everyone else's immune system to do the same thing and clear the virus from their body as well. But at the moment we don't know how this happens, and it's pretty unlikely that for an average person you would test positive or acquire the virus and then suddenly test negative. And if you're testing negative, then actually you can't be shedding the virus, because you have to have virus growing in your body and be detectable in the bloodstream to be infectious for HIV, I would say.
Amanda, good morning.
Hi, good morning. I wanted to ask, there was an article in the UK Guardian a couple of months ago that said that the new research is showing that if you're feeling better in the middle of a course of antibiotics, you should stop taking the antibiotics instead of finishing the course. And I wanted to know if you could explain why.
Yeah, the reason that people have this sort of mantra about always complete your course of antibiotics, it's based on some sound science in the sense that if we take TB as an example, one of the reasons why tuberculosis is such a massive problem, and in fact there's probably about 2 billion people around the world who are infected with TB, one of the reasons it's such a challenge and why we now have antibiotic resistance forms of this all over the place is that the drugs are expensive, they're inconvenient, they have side effects. So if people take a little bit of a drug, they feel better very quickly and then they think, oh, I'm cured. So then they stop because they don't want the expense and the inconvenience. They haven't completely removed the infection. So it then comes back with a flourish. And then they take more drugs, but those drugs now, the bug has become resistant. So they have to take some different drugs. And as a result, we then get resistance to the next batch of drugs and the next batch of drugs. And so the idea of getting people to complete a course and eradicate an infection from their body, that's the whole point of why people are urged, make sure you complete the course. Now, the evidence from the Guardian, on the other hand, the article you're referring to, is slightly different. What that's saying is, at the moment, what we do when a person has a bacterial infection is we say, right, you have, say, a urine infection. We'll give you X number of days of this drug, take this, and then you'll be better. Actually, that's based on the fact that when people take a drug, we know that if we give it for that long, we're going to cure everybody. But in fact, there are some people in the population who don't need it for anything like that long, and we just haven't looked. And so now people are beginning to go back and they're beginning to ask, well, what's the time that is actually better to give the drug for that will achieve cure in those people and minimise the side effects and minimise the cost? Those are the sorts of questions that are being asked now in order to do better stewardship with our antibiotics and also to minimise the cost and inconvenience and side effects for patients. We're not in a position where we have gold standard advice for everything yet, though. So the best thing to do is to follow the advice of your doctor, who should already be giving you the minimum duration of antibiotic exposure that you need, and tailoring your therapy accordingly. But certainly these questions are being asked, and people are looking to minimise the exposure that people have to antibiotics because there are always side effects.
Okay, thanks so much for that question, Amanda. Much appreciated. We've got enough time. Let's squeeze in one more. Andre, can you open your question for us?
I just want to ask, once you open up a good bottle of wine, all of a sudden you just have wine flies coming from where?
I know what you mean, because I do this. You open a nice bottle of Shiraz, and within seconds it's full of fruit flies, isn't it? The answer is they're all over the place, and they have an exquisitely sensitive sense of smell. The antennae on the flies are decorated with nerve endings, which have these chemical receptors on them for the very same volatile agents which are given off by wine, because these flies would normally track down fruit, rotting fruit, and fermenting fruit that's dropped on the floor. They go and drink the sugar that's being released by that fruit. They lay eggs on the fruit, and then more fruit flies are born. So their nervous system is programmed to detect those chemicals at very, very low levels and to fly around detecting when they are flying upstream. So they can compare between their two antennae the concentrations of those volatile chemicals in the air, and as they fly backwards and forwards, they can work out when they are flying towards the source. And they can smell these things from very great distances away. And they will hang around in the environment, and as soon as they pick up that smell, they think, aha, that's lunch. That's my chance to go and get a sugary meal, meet some other fruit flies, make sweet fruit fly love, and lay eggs. And they're looking to do that in your wine because they think the wine is some fruit. Because at the end of the day, it came from fruit, didn't it? It was grapes.
Absolutely. There you have it. Thank you, Andre. Thank you so much, Chris. Love your work. We'll do it again next week.
All right. Thanks, everybody, and see you soon. Bye-bye.